Hello everyone. So I will be showing today how to do a one-way ANOVA and how to add those little letters on top of the error bars, which will indicate the statistical significance. And I will show you how to do that in R. So this is your R Studio, which is a console which was developed for R. So the original R that you can download from the website is gonna look like this. And it's very inconvenient to work in, like in my experience, because like every code you're gonna run is gonna pop up in a new window, and it's just very hard to keep track of what's going on because you have so many new windows that's opening up. Therefore, they created this different extension to the R, which is called R Studio, which is basically using the same principle as R, same codes and everything, but it's just more user friendly. You have your R script on the top left over here where you can write all of your codes. And when you click enter, the codes won't run. So you can add more codes and stuff like that. If you want to run a code from R script, you can just click run over here. If you write your code in the console, which is located on the bottom left corner, you can run the codes by clicking enter. So if you're gonna run the code and click enter, it will actually run the code. So let me just clear that up. So on your top right is your environment, which is where all of your data sets that you might have imported or your results from your statistical analysis is going to be located. And then the bottom right corner is where you have your plots, for example, different packages that you can download and files in that working directory that you're working in. So just a quick disclaimer, I am not a pro when using R. I learned it myself and I still learning. I don't know a lot of things. So if you guys gonna have a question, there's a big possibility that I'm actually gonna have to Google it, and it's fine. So if you are willing to learn R, I encourage you to do so because it is much easier to use R to work with the large sample sizes. So in Excel, it's just very difficult to organize it all, but in R, it's going to be much more user-friendly if you have a lot of different samples. Furthermore, I think creating plots is better in R, in my opinion. I like how they look more. Like, for example, from last week, you saw that doing a Factorial ANOVA and creating the bar graph was just, it's very hard to interpret. So R will help me to kind of create a better plot for these statistical analyses, for example. So as I said, Google is your friend when using R, and there's actually this amazing website that they created, which is called rseek.org. And this is basically Google for R. So if you're gonna type anything, so for example, how to do an ANOVA, it will find it for you, and it's just all going to be related to R. So you don't have to say like in R, and then the Google might give you some like nonsense on there. Like this is all strictly R. And then the R is like such a big community for help, and you can find a lot of examples, a lot of videos of how to use R. And there's a big possibility that if you don't know how to do something, you will figure it out very fast because there's just so many examples that you can find. R is also used in many different disciplines. I know that they do modeling with R, like they use it in physics too, obviously statistics. So just there's a lot of different things that you can do. And if if you can find how to do something in R, you can also just hand code it yourself. So it's just a lot of freedom that you can do. And I mean, I never hand coded anything myself. I don't think I'm at that level yet, but just the thought of it makes me feel good. But anyways, with that quick disclaimer, I would like to start and I'll just show you how to do a one-way ANOVA. And as I said, I'm just gonna do a quick plot on how to add those statistically significant indication marks on top of the error bars. So the first thing you want to do is you want to set your working directory, because when you open R, it's going to have your working directory set to something random like your disk C or your desktop, and that not might be necessarily where your file of interest is located. So you want to set your working directory where the file is. So to do that, you write your set working directory function or set WD, you open your parentheses, and then you're basically going to put your working directory of interest. And you can find this working directory if you just go to file that you want to find and you click properties, and you can just like select that working directory where it's located. So now that you have done that, you can run that code. And then once you run the code, nothing happens. But then if you want to open the file in that working directory, you'll be able to do so because R is already known where to look for that file. So to open the file, you're gonna name a file whatever you want. So I just named it data, and that's how you're going to be referring to that file later on throughout the R statistical analyses. So you write your name of the data of however you want to name it. You can name it ANOVA or whatever, and then you write the little arrow, which will indicate that this file is going to be your file of interest, which is located in your working directory. So one thing that you want to do is when you have your regular file with ANOVA, which might look something like this. This is what mine looked like, and it's the data from last week that I showed you guys. I rewrote it basically where I put just two columns, one with concentration, one with the cell viability, and I just put like different concentrations over here and different cell viabilities, and it's just both in two columns, so it'll be just easier to read with R. And then important thing is that I like to save my file as a CSV. So when you click Save As, this BC, you just click the comma delimited value option. And R can read a lot of different files. It can read Excel. For me personally, I just prefer it to be a CSV. But you can, as I said, you can save it as Excel. But then you have to indicate that it's an Excel file instead of the CSV, like I did here. So you're gonna write your name of the file, the arrow, and then I'm saying read CSV, and then I open my parentheses, I put the name of my file, and I click comma, and I like to indicate that there is a header in my file, so I put header equals true, and I do have a header, it's the console and cell viability header, and then you click, not console, concentration and the cell viability columns, headers, and you click run. So when you do that, it ran the second code too, but when you do that, nothing will happen, but your data will automatically generate in your environment. And what I like to do is I like to run a next code, which calls string, which will kind of show you what kind of variable your columns are. So if you click run to that, string, open parentheses, the name of your file, which I named data, it will tell you that your cells is an integer or basically a continuous variable, and concentration is also an integer or continuous variable. And if you remember, that is not true. We have our concentrations in categorical variable. So you have your 0, 15, 30, and 50. So they're different categories. And whenever if you remember to have a one-way ANOVA, your independent variable has to be categorical. In R, categorical variables are represented as factors, so factor variable. So you want to make sure that before you proceed, you can change your concentration to a factor variable instead of the integer. To do that, you're gonna basically write the name of your file, which you named data, and you're gonna put the $sign and the column that you want to change, which is in this case is concentration. Then you're gonna put again your error. And as you can see, I'm rewriting the code that I already have on the top here, but I just wanted to show you how it will look. Then you write the code is factor, open the parentheses, and then your X variable is gonna equals to data, $sign, concentration. You can just write concentration. So instead of the data $sign concentration, you can just write concentration, which should generate over here. However, from my previous experience, sometimes I would like misspell my data in Excel. So I would forget to end in O in concentration. And whenever I would write like just concentration with no like normally spelled, it would say that there is no such variable, and it would give me a lot of errors. And I would get very frustrated because I know that the variable is there. I'm looking at the data. I just wouldn't catch the fact that I misspelled it in that actual data. So when you actually write your data with the $sign, it's much easier to not make that mistake because you only have a few options and it's generated straight from that data file. And then you click OK. And after you did that, I ran the string code again, which will show me like whether or not the R was able to change the integer to factor. Click run. And then as you can see, now your concentration is a factor with 4 different levels, which is 0, 15, 30, and 50. And that is what we want. And then the next step, I just do a code attach, and it's basically attaching the data to that R console so we can work with it later. So the next step is how to do an actual one-way ANOVA in R. So first step would be to install packages. R has a lot of packages that already go with R when you download it. So you can just say install.packages, open the parentheses and the name of your package, and it will install the package directly. Or you can also go to, for example, a website called CRAN packages. And it will just give you like different packages that you can also install, and just there are so many of them. Like you guys can see, like it's just endless amount of packages. But everything that we need should be already with your R. So if you click install packages and then the package of your choice, for example, we need package stats 19. It should install it. Okay. And for some of the stuff that I was doing here, I had to Google what kind of package to use to run a test. So, don't feel overwhelmed that like, oh, like how would you know what kind of packages? And there's just like so much stuff. Like you just Google everything. And I mean, I'm not, as I said, I'm not a pro here. So like a lot of the stuff that I'm doing in R, I'm always referring to Google or to that RC website that I told you about. And it's just very helpful. But anyways, once you install your package, you again write library and the name of the package. And it will basically make the package available for you to work with. Next step is to do your one-way ANOVA. And again, I'm going to name my one-way ANOVA file aov.res. And you basically write the name, whatever you want it to be. And then you do an error. And the code for ANOVA is analysis of variance, or AOV. You open the parentheses and you basically say what your dependent variable is. In this case, it's our cells. Squiggly line, I forgot what it's called, but you do the squiggly line and then you say that your independent variable is concentration in this case. And then after you did that, you click run and nothing happens. However, if you notice, your global environment now has aov.res, which is your ANOVA. So you can either like double click on that and it will just kind of generate it here, which not very helpful because you can't tell anything. Or you can just do a code, ANOVA, parentheses, and the name of your ANOVA file, which in this case we have aov.res. We run it and we get our p-value. In this case, ANOVA says that our p-value is less than 2.2 times 10 to the negative 16, which is very significant. And you see those 3 different asterisks here. And you can set a code which will tell you like a specific p-value of interest, but I don't have that code in, so it just says less than 2.2 or whatever. But there's a code that will tell you like exact p-value if you want. But we're just gonna go with that. So we see it's a significant, but as you know, in ANOVA, you don't know where that significant lies. Like it just tells you like, okay, overall the data is significant, but now you wanna figure out where exactly that significance is. So the problem you have with that is, people might think, oh, I'll just do t-tests between different groups. However, you cannot do a t-test with the same data multiple times because there's a problem of alpha inflation, or you're more likely to make a type 1 error. So in order for you not to have that alpha inflation, you have to have some kind of p-value adjustment. One of those adjustments is Bonferroni adjustment, which I will be using in this tutorial. And a test that is, you don't want to do a t-test and then say, oh, and do the adjustment. There's actually a post hoc test that will account for the alpha inflation and do the adjustments for you. So one of those tests that I'll be talking about today is Fisher's least significant difference test, or LSD. And you can do that test in R, which I'll show you how to do, and it will just basically tell you where exactly the significance is between 4 of your different columns. So to do that, you first have to install your package, which is called agricole. You run that package. Then, as I said, once you run the package, you have to actually pull it up and make it available for you to work with. So you have to write library agricole, which is the name of the package you just installed, and then you click run. So now we can run our Fisher's least significant difference test. So I'm going to name the test LSD underscore A. And again, you can name it whatever you want. And we're going to say that this test is equal to your LSD test function in R. So you write LSD.test and then open the parentheses. And in parentheses, you write Y is your dependent variable, which is cells. Treatment is your independent variable, which is concentration. Then based on your ANOVA test, if you look at the formula of how to calculate an F statistic in ANOVA, there are multiple components, one of which is DF, or degrees of freedom, degrees of freedom error, and then you have to tell R to calculate that, or basically extract it from the ANOVA that you already calculated. And you just write the name of your ANOVA test that you created earlier, which I said it was AOV.res, and you put a $sign and you indicate that you want to extract your DF residual. And then there's also MS error that also comes from your formula of how to calculate the ANOVA. And in order to find that, you have to divide the deviance of your ANOVA, and you have to divide it by the DF residual. And again, these two, like, you can Google it, and this is basically the mathematical formula that you have to refer to. And if you just Google, for example, I can just show you ANOVA formula. Like, you can see over here, there is within and between and the total source of variation. And you have your degrees of freedom, mean squares, and this is basically like how you find all of those different things. And R is just basically referring to that mathematical formula. So once you put that, you click comma, then you indicate your alpha, which in this case we're going to go with 0.05. Then you want to indicate what kind of p-value adjustment you want to use. In this case, I'll be referring to Bonferroni adjustment. Then you want to say that you do want to group them by group or by concentration. So you say group equals true, and then you say console equals true, which basically say, yes, console, please pull up the data and show me what it is. So one thing you notice is that it kind of goes like over here, like in the middle, versus just being in one line. And I just wanted to show you that I purposely did that because you can write the whole code in one line, but then it's just going to be very long. However, if you just click enter, it automatically like go over here, which is creates like more readable code, so you can quickly read it without scrolling, through the whole code. So once you wrote your code, you're going to click run, and it's going to tell you basically the significant letter notations, which we then are going to use for our plots. So as you can see, our 0 and 15 have the same letter. That means that there is no statistically significant difference. However, both 30 and 50 have a different letter, which indicates a statistically significant difference. So different letters from each other are statistically significant. Same letters are not statistically significant. As you can see, there's no actual p-value in between, but you can write a code that will actually give you the p-values, exact p-values between those, but we're not going to do that because I just wanted to show you how to find those letters in R. And now the next thing you want to do is you want to indicate that these groups are corresponding with different concentrations. So whenever we're going to be making a plot, you want to indicate that concentration 0 is letter A. Concentration 15 is letter A. So as you can see over here on the left, there is no word saying concentration. There is no label, basically. So we want to add that label so R can then refer and easily add those letters to the corresponding concentrations. So to do that, we have to install another package called dplyr, and you say install package dplyr. You're going to click run, and if the window pops up, just click yes. And then you're going to open that package, actually pull it out from your library, and you're going to click run to the code library, open parentheses, dplyr. So now it's available to you. And basically what you're going to do is you're going to say that you're going to name that grouping ascend A, which you will then use to make your plot. So you will refer to those ascending letters as the name ascend A. You can rename it whatever you want, just that's the name that you're going to refer to those statistically significant letters later on. So you say name equals to that test LSDA that we just conducted, and specifically your different groups. And those groups, as you remember, are those letters. And then you write the %, error %, which in our language basically means then. So it's saying take those groups and then group them by the row names of those groups, and then arrange them by those row names. And I will kind of show you what it's going to do. So you run that code and then you print it. So you want to see whether or not it actually did it. So you click print and then the name of your of that code that you named it, in this case is ascend A, and you run it. So now, as you can see, you actually grouped it by different row names. So A is corresponding with 0, then the second A with 15, B is with 30, and C is with 50. As you remember last time, we didn't have those row names. Like it was just kind of random, and R wouldn't be able to assign those different letters to those different concentration. But now since we grouped it by different row names, once we actually tell, okay, add those ascend A name of your of this different row names grouping, you will be able to assign those letters to the corresponding bars in the bar graph. So before we actually make the bar graph, we want to find the means and standard error. So it can put the error bars or it can put just the means of your bars in the plot. So to do that, you write the name of your data, how you want it to be named. In this case, I just wrote mean SE_A. You can name it whatever you want, and then you click equals. You're going to select the data that you want to find the mean of. If you remember, this is the name of our data, which I named data. You're going to click, where is it? Data, and then you're going to group them by concentration. And then you're going to summarize the average of your cell viability, average of A equals to means of cells, and standard error. And again, standard error is going to be right here. And this is just a mathematical formula, how to find your standard error. So it's the standard deviation divided by the square root of cells in this case. And you're just going to run that code. And you want to print the code so you can actually see whether or not it did that. So now you have your averages and your standard errors. And again, you just want to attach that. So now the R is referring to those means and standard errors once you're going to be making graph. So now when you're going to be making graph, if you want to use those means, you're going to say graph, and then you're going to use mean SE_A, because that's the name of your means where you calculated. However, if you want to use your letters to add on top of your means to indicate statistical significance, you're going to use ascend_A, because that's where you actually group them. So it's just a matter of creating your names and then using them properly. And now we're going to start making a graph, and you're kind of going to see how it all goes together. To make graph, there's this amazing package which is called ggplot2, and you're gonna install that, you're gonna run it, and then it's gonna install the package, and you actually have to pull it up again from the library ggplot2. So now the first step is you wanna add your basically a raw graph. So it's not gonna have any bars, probably the labels are gonna be wrong, but it's just gonna be your raw idea of what the graph is going to look like. So I'm gonna make that graph P1, and I'm gonna say that P1 is equals ggplot function, which is your plots. You're gonna open the parentheses, see that's where the name mean SE, this is where our means come in. So you're saying that you're gonna use those means from this name right here that you created. Then you're gonna use the function AES, which then you open the parentheses and you write the concentration for your X variable, and for Y variable, you're gonna use your averages of the cells. Now when you run that, you can print that P1 plot, and you're gonna run it, and on the bottom right, you're gonna see basically a rough draft of what your graph looks like. And as you can see, no bars. On the y-axis, you have your average underscore A, which you don't want. So there's quite a few things that we have to modify, but this is going to be our next step. So now you guys basically going to be adding on to that graph. So first you have to, again, come up with some name. I'm gonna name it plot A, and I'm gonna say plot A is equals that P1 graph, which is right here in the bottom right, plus function geometric bar, which is gonna add you bars to your graph. You open the parentheses, and because that P1 already has your means in there, is just not shown, you don't have to indicate those means again. But when you open the parentheses, you basically have to add all of this stuff, which is basically saying what kind of color do you want your bars, why do you want them, and all kind of different stuff, which I had to Google, I don't know what's the normal width in R of the bars. So I just had to look it up. So you're just saying, this is the width, this is the position where you want it, this is the color, and you just run it. And then if you're curious to see whether or not it did what it did, you can write in your console plot A and just click enter. And then it's gonna show you, okay, it added the bars with the correct means. So next thing we want is to add your error bars. So now we're gonna create a different name, which I'm gonna say plot B, and I'm gonna say that plot B is equals to plot A over here in the bottom right, plus geometric error bar function. And then you're gonna open the parentheses, again, the function AES, which kind of helps you to create those graphs. That's what the function is for. Open the parentheses, and you basically gonna indicate your maximum error bar and the minimum error bar. If you remember in Excel, to create error bars, if you click custom, it has the min and max function. Same thing here, you're just gonna show where those error bar maximum and minimum is. And again, it's pulling it from the data that you already did from the average A. We did it in the beginning, remember in the summary over here. So it's basically saying, use this to find your maximum and the minimum, and against the position, the width of those error bars. I also had to Google it. I don't know the position, what is the correct position of the error bar. So you just run it, and then if you want to see whether or not it added those error bars, you can again write plot. In this case, it's plot B. Click enter, and as you can see, we added our error bars. So next thing we want to do is add our title. So we want to change it, instead of average underscore A, we actually want to put cell viability. So you say plot C, or whatever name you want to go with, is equals that plot B that we already have, plus you're going to add labels or labs function. Open the parentheses, you can say that you want to change the title. And then for x-axis, you want it to be named concentration. And for y-axis, you want it to name cell viability. And then you're just going to run that. Again, if you want to see whether or not it did what it did, you can write plot C and enter. And you can see that it actually changed your y and x-axis. Okay, last step is we're going to add letters to our error bars. So as you see, like there's a lot of steps prior to adding those letters, but the most important one is actually conducting this post hoc test, which will tell you where the differences lie. So to add those error bars, you create another plot name, which is plot Z, or whatever you want it to be, equals plot C, which is already over here, plus geometric text. Open the parentheses again, AES, open the parentheses. For x-axis, it's concentration. For y-axis is going to be your averages plus the standard error, comma, and then you want to add your label. Your label is going to be as matrix, you open the parentheses, and then you're going to use those labels that you created and you indicate what labels you actually want to put. So in this case, we want to put groups. So if we go back, let me see. So over here, as you can see in the console in the bottom left, we're saying that we want to use labels from the ascent underscore A, which is right here. This is what we named it. Remember, this is the name that you used. And then putting the $sign, which we want to indicate what we actually want to put. You can put row names, you can put data underscore $sign cells. But in this case, we want to put groups on top of our error bars. So when you do that, you do comma, and then again, you're just doing the position, the width, and all of that stuff, and you run it. Now, our final graph is you're gonna say either plot D, or you can say print plot D, same thing. And click enter. And now you can't see the letters, but if you click zoom, this is your graph. There's a lot more stuff that you can do with your graph. You can change the color, the width of your bars. You can do this, this, and that. But this is just basically raw graph that you can get with R with the letters on it. Okay. So I hope that was clear. I know that there was a lot that for many of you guys might be the first time like seeing all of these codes, but I think it's a good experience to learn what R looks like. And once actually adding the letters, it's not that difficult. It's just like remembering, okay, what name did I use? What name did I use there? What name did I use there? And if it helps you, you can also write it down or, use names that you can remember more easily. Okay, so next thing that I wanted to show you really fast is I'm gonna show you this code as well, which is basically gonna save your R script in a PDF file, or in this case, HTML. You can also change it to PDF. So if you run this code, and this is the name that you wanna go by, so if you run this code, you will actually save these codes in the HTML file, because if you just copy them to Word, it's not gonna keep the same colors, the hashtags and all of that, so it'll just harder to see. But if you run this code, it will actually save it to a next file, and it will be easier for you to go back and see what the codes look like. Okay, so now let me show you really fast how to do an interpretable graph for F statistic or Factorial ANOVA specifically. As you remember, so let me see. This is our ANOVA. This is our factorial graph. Factorial data. And this is the graph that we got. So as you remember, it's like very hard, like you don't really understand like what is happening. Like you just have to think about it a little bit longer. So you can, again, you have to rewrite your statistics in like where you have just like columns. And let me see where it was that. Okay. So this is how I rewrote it. So basically, instead of just using means, I added like normal data. And I said that high concentration, and then I used 3 different cancers. Because as you remember, we're trying to see whether or not cell viability changes depending on the concentration of the drug and the type of cancer cells that we're using. So we have lung cancer, breast cancer and kidney cancer. So we're saying at high concentration and then 3 different cancers. And these are our means. Means for lung cancer, high concentrations, not means, but just the values. Values for cell viability at high concentration for breast cancer, high concentration for kidney cancer, and then medium concentration. And you're just kind of repeating it. So we have 3 different columns. And again, just save it at the CSV file. And now we're going to go to R. Again, we are, if you click Control and L, it will clean your console. So we can just start from the beginning. Then let me clear the plots as well and the environment with this little broom over here. So we're starting from the scratch. So again, you're gonna set your working directory, and I have the same working directory as before. And then you're gonna name your file, and you're gonna say read CSV. I name my file FS, and that's how I'm going to be referring it in the future. So you read CSV, and this is the name of my CSV file, which contains the data that I want. You run it, and then I just want to open it and see how it looks. I'm going to be adding a lot less stuff than compared to the regular ANOVA, because I just wanted to show you the graphs. But you still want to make sure that you run your string factor to make sure that these are actually represented as factors and not in continuous variable. So before that, install the package dplyr, which we will use later. So I'm installing that package, which will help us with the plots and everything. Okay, now I'm going to check for my data. As you can see, our cell availability is integral, and the concentration cancer is this variable called CHR. I want it to be a factor again, because factor is basically categories. So again, I'm using S factor, open parentheses, and then I indicate the data that I'm going to do and exactly the column that I'm interested in. So I'm interested in changing concentration to be S factor, and then cancer to be S factor. So then you can do maybe the SCR function again with the data to make sure that R did what it's supposed to do. And if you run, okay, well, I don't know why it's not doing it, but we're gonna pretend that it did. So we can move on and actually do the graph, because I know it's taking some time to go through that R tutorial. But we're gonna use the CHR, and we're gonna say that it was S factor. And we're gonna install next the package called DevTools, which is located over here. Click yes. And then we want to install a different package within the DevTools package, which is represented in this code over here. And then we're just gonna click enter. Okay, so you see it's installing like a lot of stuff within one. Okay, so we have this error, so that means it's done. Now we want to install our package ggplot, which will help us with the graphs. And we want to pull that package out of the library and pull that package out of the library, which comes with the previous packages. Okay, as you can see, I'm doing a lot less compared to ANOVA, but I'm kind of just wanted to focus on the graphs, the plots that you're going to do. But if you Google the Factorial ANOVA, there's a lot more steps that you want to manipulate your data with. But so first, I'm going to show you how to do a box plot. You use a function gg box plot, open the parentheses, the name of your data file. You can put X is your concentration, Y is your cell viability, or your dependent variable is cell viability. And then you want to group them by color. So it's going to be cancer. So different colors going to represent different cancers. And then you just put in your different palettes. As you can see over here, I just decided to do everything in one line. And you have to like scroll to get to the end of the code. But then those colors you can find on our website, but I just decided to use those different ones. And you click run, and this is your graph. So as you can see, you have 3 different concentration, and you have 3 different cancers, and they all represent with those different box plots. This is a made-up data, so they don't look very pretty, but like with the normal data, like your box plots would look more pretty, I guess. And then you were doing your second graph where I wanted to actually color them by concentration instead of cancer. So you're gonna say GG box plot, you're gonna use your data that you want to go to. X is going to be your cancer, or your x-axis is your cancer, Y is cell viability, and actually color, you're gonna go by concentration. And you're gonna run it. So now, as you can see, instead of coloring by different cancer types, you have an opposite where you have different cancers on your x-axis, different concentrations in 3 different colors. This is basically your basic box plot that you can do. To do a line graph, which will show you the different lines for different cancers or different concentrations, you can do the GG line graph. Again, data that you're referring to, your x-axis is going to be concentration, y-axis cell viability, and then we're going to color them by the cancer type. But then you want to make sure that you add the means and this function called dot plot. And then again, using different colors for your palette. These are just the ones that I used to, I decided to go with. I'm going to run them. So as you can see, now you have your line graph. And again, this is a made up data. So it's like a little bit weird to see like so many, like there's an outlier here, outlier there. Like in the normal data set, it will be more prettier. So you have your concentration, the x-axis, cell viability on the y-axis, and then they color by three different cancers. And then if you want to do the opposite, where you do the line graph, but they color by different concentration, you basically do the same thing. And instead of color, you write the concentration, where the color was cancer, you write the color concentration, and where the x-axis were concentration, you write cancer. And you basically repeat the steps. And as you can see, now you have different lines which represent different concentrations, and also you have different cancers which represent on your x-axis. Okay, and then you can do ANOVA, which I won't show how to do, but basically a similar process. There's also a assumptions test that you can do. As you remember, when I was giving a presentation on ANOVA or t-test, I said that there are specific assumptions that you have to meet in order to do the test. You can test for these assumptions in R. There are specific codes for this. For example, you can have your Shapiro-Wilk test, which is a test for normality, and this is the code for that test. And then there's other normality tests that you can also test for. Okay, well, I hope this was helpful. I know this was a lot, but hopefully you guys can see that, it's not that complicated as long as you put the right codes in. And as I said, that's, for me personally, R requires a lot of Googling because I'm still learning. But when actually the packages work and my statistical analysis work, it's very nice. It's very nice to see that, oh my God, I did it. So it's very rewarding. So please email me if you have any questions. If you do want to play around with R, I can send you my codes, and so you can basically use them and see how it works on your computer. And in general, if you have any questions, please reach out to me and I'll try my best to answer them. Thank you.